Okay, in this video we're going to do section 2.6, optimization, and this is problem number 21 on page 197. So to read it, it says, an open rectangular box. So open is important, it has no lid on it. It's a rectangle, so I know the area is length times width, and it's going to be constructed by cutting square corners, okay, square is important, out of a 16 by 16 inch piece of paper, a piece of cardboard, and folding up the flaps. And here's the picture below. So what I'm seeing is I have a two-dimensional object, and by cutting it and folding up the flaps, I'm going to make it a three-dimensional object. Okay, two-dimensional objects have area, three-dimensional objects have volume. And so they want us to find the value of x for which the volume of the box is as large as possible. All right, so we need to think about this project. The textbook has annotated this a little bit differently than I would have. So I agree that this width is a 16, but I would not introduce another variable. So what I would like to do is identify all the sides and all the pieces using x and either x or a number. So if I know this whole piece is 16, then once I cut it, what they called w is really 16 minus 2x. So all the sides, once they are folded up, will be 16 by 2x. What will the height look like? Well, you fold up by x, so therefore when you make your box, so here's the side of your box, and it's going to have a height of x. So what's volume? Volume equals length times width times height. Okay, so each of these pieces right here, that's going to be the width. So let's call that my width. So that's 16 minus 2x. And then my length, when it's folded, is going to be right here. So the red's length, width. So my length is another 16 minus 2x. And then my height is going to be the fold, which is x. So my volume that needs to be maximized is going to be 16 minus 2x squared times x. Now let's think about this for a second. This volume is our objective function. So this is the objective function. Notice that the objective function only has one variable, and that variable is x. So up to this point, we have been constraining our problems, and that constraint has been used in the objective function to eliminate one of the variables. Well, I don't need to use the constraint to do that this time, but I still have a constraint. It's an implied constraint. What is that? Well, let's think about this. If you're cutting your edge, so let me talk about constraints using the red. In order to have a box at all, 16 minus 2x has to be greater than 0. Does that seem reasonable? If I have a side of 0, I don't really have a box. So can we divide everything by 2? Because let's reduce this. Divide this by 2, divide this by 2. If I divide that by 2, then I know that 8 minus x has to be greater than 0. Adding x to both sides, I know that my 8 has to be, excuse me, let me do that the other way. My x will have to be less than 8. So let's look at that. So if my x is less than 8, so I'm just reorganizing this now. So I'm adding 8 to both sides. So let me turn my pen back on. So what I have is x is 8 is greater than x, so therefore x is less than 8. So that is my constraint. So just keep that in the back of your mind. I still have a constraint, but I'm not using it the way I've used them previously. Okay, so we're starting to get ready to set up our problem. So we're going to go on the next page. I'm going to write this out nice and neat so that we can get to work. Okay, so we want to maximize volume, and volume equals length times width, they're both the same, so I'm just going to square it, times the height, which is x. So we're going to need to FOIL this first piece and then multiply through by the x. So to do that, I'm going to get volume equals, and I reorganize my equation, 4x cubed minus 64x squared plus 256x. That is our volume. Find the first derivative, and you get 12x squared minus 128x plus 256. Set that equal to 0. You're going to need to factor it. So the first thing I'm going to do is factor out a 4, that's the greatest common factor, and I'm going to get 3x squared minus 32x, and let's see, 256 divided by 4 will give me 64, so plus 64. So what multiplies to 64, and well actually what multiplies to 64 times 3 and adds to negative 32. So you're going to have to do some hard factoring. So take a piece of paper out and try to do that, and I'll give you a second to think about that. Okay, I hard factor by decomposition, and doing that, I get the following: 4 times 3x minus 8, x minus 8. Set my factors, these are my factors because they have x's in them, to 0, and I get x equals 8/3 and x equals 8. Okay, I want you to notice quickly that x equals 8 has to be rejected because it doesn't follow our constraint. So my answer seems to be x equals 8/3 for my length of my cut. But before I know that for certain, I have to take my second derivative. So we'll do that on the next page. So knowing that v primed equals this expression, my first derivative, my second derivative is going to be 2 times 12, 24x minus 128. I said the CV, the critical value, was x equals 8/3. So let's evaluate my second derivative at x equals 8/3. So that means wherever I have an x, I'm going to plug in 8/3 minus 128. 3 goes into 24 6 times. I get 48 minus 128, which is going to be less than 0. Therefore, I have a function, my volume function is going to be concave down, and therefore the CV of 8/3 equals a max. So you can plug in and you can get all your dimensions, but that is the end of our problem.